Hello everyone and welcome to this tutorial in which we will show the equivalence between weak mathematical induction, strong or complete mathematical induction, and the well-ordering principle using this circular flow to establish the equivalence of these three axiomatic statements. Okay, and so in fact what we'll be assuming as axiom is the weak mathematical induction, from which the other two then will follow. Okay, and that's all assuming the standard model of Pinot arithmetic. Alright, so basically let's just go through the statements just to remind ourselves what we're trying to achieve over here. And so the principle of mathematical induction states that for any predicate P about the natural numbers, if the base case is true, right, that's this P of 0, and the induction step holds, the step over here, then the predicate P of n is true for all natural numbers. Then it follows that for any number n, P of n is true. Alright, and so for strong induction, this is pretty much the same thing, except for the stronger requirement that if we want to prove the induction step, then we need the additional criteria that all the preceding predicates P0 up to Pk are all true, preceding that predicate at index k plus 1. Alright, and then finally we have the well-ordering principle, which states that every non-empty set of positive integers contains a least element. Such a obviously true statement should be considered an axiom. Alright, but we're just going to prove it from the mathematical induction principle instead. So yeah, let's get to it. So to derive complete induction from induction, suppose that induction holds. For some arbitrary statement S of n about the natural numbers. Okay, and then let T of n be the statement that all preceding statements or predicates on the natural numbers for that arbitrary statement holds. And so our approach here is to define this new statement that talks about all the statements S over the indices ranging up to n, and then to apply the induction principle, which is what we assumed to be true, to this new statement. To do that, we need to consider the base case, but that's quite simple because all that we have to notice is that T of 0 coincides with S of 0. But we already know that S of 0 holds from the base case of the induction hypothesis, from the induction principle, which is our assumption. Alright, therefore T of 0 holds, because T of 0 is just a statement that all the preceding statements of S holds. And in this case, we've just restricted the index to 0. So suppose for the induction step that T of n holds, and we want to show that T of n plus 1 holds. Okay. But since T of n holds, we know that S of 0, S of 1, all the way up to S of n holds. Because that is what the statement T of n means by definition over here. Okay, but since S of n holds, we have that S of n plus 1 holds from the induction step of the induction principle, which is our assumption. Thus, S of 1, S of 0, S of 1, and all the way up to S of n, and including S of n plus 1 holds, which is basically the same as saying that T of n plus 1 holds. Okay? But this basically is the same as saying that complete induction holds, because complete induction says that the base case should hold, and all the preceding cases for our induction step and that index value. Okay, because we've now showed that this is true. T of n holds for all n that are natural numbers. Therefore, we can say that complete induction holds. Okay, or at least follows from weak induction. So next we will use complete induction to derive the well-ordering principle. And to do that, suppose that complete induction holds. This is our assumption, which we will use later in the proof. And let S of n be the statement that if A is a subset of the naturals containing the value n, our index from the statement over which we predicate, okay, then A contains a least element. We are not necessarily saying that n is the least element, we are just saying that A contains a least element. It may happen that n is that number, okay, as we'll see in the base case. But what we're about to do now is to show the base case, because this is what we have available. We have the induction, the principle of complete induction available to us. So for our base case, we want to show that this statement is true, which is the statement that if A is a subset of the naturals and 0 is in A, then A contains a least element, which is true because clearly 0 is the smallest number for any positive set of numbers. Okay, so the base case holds. Okay, so we've established the base case, but now for our induction step, we assume that S of 1, S of 2, all the way up to S of k holds. And we want to show that s of k plus 1 holds. So let's look at the statement s of k plus 1. And that's the statement that if a is a natural, if a is a subset of the natural numbers and contains the number k plus 1, then a has a least element. Okay. So we have two cases to consider. Okay. If a contains any number that is less than k plus 1, then we can see from our induction hypothesis that this statement is true, because these numbers, that m would then be less or equals to any of the indices in this statement list over here. Alright, so that's our first case. If a contains any number, say m, less than our current index k plus 1, then a has a least element from our induction hypothesis. Which is the statement over here that S0, S1, S2 up to Sk holds. Okay, because these statements all say that the set A contains a least element. Alright, so this statement says also that A contains a least element. Okay, and then that's the first case. The second case is that if A contains no element or no number m, or we don't need to give it a name, but just no number less than k plus 1, then in fact k plus 1 is that least element. And therefore A does contain a least element. So basically we've just showed the statement is true for any k that is a natural number. And the statement that we've shown to be true boils down to the well ordering principle, which says that for any subset of the natural numbers, we can always find a least element. So we can then conclude that the well ordering principle holds. Okay. And so I think that's a really nice result. So here we will show that the well ordering principle implies the technique for mathematical induction. Okay, so to do this, assume that the hypothesis of the induction principle holds. That means for some arbitrary statement S about the natural numbers, we have the following. The base case is true, and also the induction step is true. And what we would like to show is that the consequence of the induction principle holds. So we want to show that the statement S of n is true for any natural number. Okay, so to do that, let us consider a set Q which keep track of the indices for which the induction principle hypothesis is true, but for which the conclusion does not hold for all natural numbers. Okay, and then what we would like to show is that Q is in fact empty, and that this cannot happen, so that if the induction principle's hypothesis is satisfied, then the conclusion for the induction principle should also be satisfied. Okay, in other words, there are no statements for which this happens. Okay, so we're going to reason by contradiction that Q is not empty, and we will suppose that Q is in fact empty, which will allow us to use the well-ordering principle. So by the well-ordering principle, there is a least element. Suppose that element is called M, and then it obviously has the property that it is less than all the numbers in Q. Sorry about that. Such that M is less than T for all T. Okay, but notice that this M that we found, this least element, cannot be 0, since in that case, if it were 0, the statement S of M would be true, which would contradict the fact that M is in Q. Okay, and also since the predecessor M minus 1 of M is less than M, and M minus 1 is not in Q, it is true that S of M minus 1 holds. Okay, because M minus 1 is less than M, but M is the least element of Q, therefore M minus 1 is not in Q. And also that Q is the set that only keeps track of indices for which the statements S of n does not hold, but M minus 1 is not in Q, therefore the statement S M minus 1 does hold. Okay, and what we want to show now is that from the assumption, the hypothesis of the induction principle, that means from the inductive step 2, since S of M minus 1 is true, we have that S of M holds as well, which actually contradicts that M is in Q. So our assumption that Q was empty cannot leads us to this contradiction here. So, it is actually the case that Q is empty. Okay, which is a good thing for us, because this means that for all natural numbers, if the statement satisfies the induction principle's hypothesis, base case, and the induction step, then the statement holds for all natural numbers, which means that induction principle holds. And that's a really good thing for us,